All right, let's dive right into this explainer. Today, we're unlocking the fascinating mathematics of circles. You know, it's so easy to look at a circle and just see a simple round shape, right? But beneath that smooth exterior is this incredible world of perfectly balanced geometry. We're going to see exactly how to transform these abstract concepts into real-world tools that you can use for everything from basic math to literally complex landscaping.
Here's our roadmap for today. 1. Properties of circles. 2. Symmetry and chords. 3. Circumference, area, and proportions. 4. The recreational park problem. And 5. Formula summary and tips.
Section 1. Properties of circles.
So the crucial thing to understand here is that a circle isn't just anything that looks round. In strict geometric terms, it's a very specific, closed, two-dimensional curve. Think of it as a pathway, a locus of points that are all perfectly equally distant from one fixed center point. That perfect balance, that's exactly what gives the circle all of its unique mathematical magic.
And honestly, this brings up a common misconception that trips a lot of people up, because a circle must be a flat, two-dimensional shape. Everyday objects like a bouncing ball, a globe on your desk, or glass marble, they are not mathematically considered circles. No way. They are three-dimensional spheres. A true circle is purely 2D, existing entirely on a flat plane.
Now, it's really cool how we can break down a seemingly simple shape into these highly specific, measurable parts. You've got your center point, which anchors the whole shebang. The circumference is your entire outside perimeter. Then there's the radius, that's the spoke reaching from the center to the edge, while the diameter stretches all the way across, right through the middle. But then we get into the really fun stuff. A chord is any straight line connecting 2 points on the edge without having to pass through the center. An arc is just a curved slice of that outer edge. A sector, well, that looks exactly like a slice of pizza enclosed by 2 radii. And finally, a segment is the little region sliced off by a chord.
So let's see how this actually builds when we construct these shapes by hand. If you wanted to draw a perfect 60-degree sector, you can't just freehand it, right? You'd set your compass to exactly 2 centimeters to draw your perfect 2D boundary. Then, using your center point as an anchor, you align a protractor, measure precisely 60 degrees, and draw your second radius. And boom! Just like that, you've mathematically constructed a perfectly measured slice of the pie.
Section 2. Symmetry and chords. It's honestly fascinating how a circle operates on perfect symmetry. Actually, a circle has an infinite number of axes of symmetry. Any straight line you draw straight through the center diameter will perfectly mirror the two halves. And because of this, there's a golden rule with chords. If you draw a radius that crosses a chord at a perfect 90-degree perpendicular angle, it will always slice that chord exactly in half. It bisects it perfectly.
But, simply knowing a chord is cut in half isn't always enough. This brings up a really critical challenge. What if you're, say, a blacksmith or an architect, and you need to find the exact mathematical length of that chord, but all you know is the circle's radius and how far that chord is from the center? Well, we solve it by realizing that the perpendicular radius in the bisected chord just created a perfect right-angled triangle, which means we can unleash the Pythagorean theorem. Let's walk through the steps. The radius becomes our hypotenuse. Let's say it's 5 centimeters. The distance from the center to the chord is one of the sides, say 3 centimeters. Plugging that into a squared plus b squared equals c squared gives us 9 plus our unknown squared equals 25. Solving for our unknown gives us 4. But wait, remember, that's only half the chord. So we multiply by 2, giving us a final chord length of 8 centimeters.
Section 3. Circumference, area, and proportions.
Meet pi. This is the absolute magical constant that bridges the straight-line diameter of a circle to its curved outer perimeter. Whether you're using the decimal 3.142 or the fraction 22/7, this ratio is literally the mathematical heartbeat of every single circle in the universe.
And using pi, we unlock 2 fundamental formulas. To calculate the outside perimeter, the circumference, we use 2 times pi times the radius. And for the internal space, the area, we square the radius and multiply it by pi. Let's see this in action, okay? If we have a radius of 7 centimeters and use 22/7 for pi, our circumference perfectly calculates out to 44 centimeters. Now for the area, squaring that 7 and multiplying by pi gives us exactly 154 square centimeters.
But what if you don't need the whole circle? What if you literally only need a piece of the pie? Well, this brings us to a really elegant rule of proportionality. The angle of your slice, represented by theta,
perfectly scales the arc length and the sector area proportionally out of the full 360 degrees. You just take your specific angle, divide it by 360, and multiply it by your standard circumference or area formula. It's so clean, the fraction of the angle is the exact fraction of the area.
Section 4. The recreational park problem. All right, imagine you're a municipal landscaper. You've been given a huge rectangular plot of land, 63 meters long by 58 meters wide, and your job is to lay down grass over the entire park. But there's a catch. The park features 4 flowerbed quadrants tucked into the 4 corners, each with a radius of 7 meters. And on top of that, there's a giant circular fish pond smack in the middle with a diameter of 28 meters. You need to order the exact amount of grass. No more, no less.
Okay, let's break this down step by step using our formulas. First, we find the total area of the rectangular park by multiplying 63 by 58, which gives us 3,654 square meters. Next, we deal with the obstacles. Those 4 flowerbed quadrants in the corners? Well, 4 quarters make a whole, so they effectively form one complete circle with a 7-meter radius. Using pi r squared, that gives us 154 square meters of flowers. Then, the fish pond has a diameter of 28, which means a radius of 14. Squaring 14 and multiplying by pi gives us an area of 616 square meters for the pond. Finally, we just take our total park area and subtract the flowers and the pond,
Giving us a perfectly precise final answer of 2,884 square meters. That is exactly the amount of grass coverage you need to order. No guesswork here, just pure geometric deduction.
Section 5. Formula Summary and Tips.
Here is your cheat sheet summarizing the core equations. If you want the outside boundary, use c equals 2 pi r. If you want the flat space inside, use a equals pi r squared, and if you only want a fraction of either one, just multiply your formula by your angle divided by 360. You're definitely going to want to keep this cheat sheet handy to keep these formulas fresh in your mind.
But listen, if you take away one absolutely crucial tip from this explainer today, let it be this. So many people stumble right at the finish line because they plug a diameter into a radius formula, or vice versa. Always read the scenario carefully and verify which measurement you are actually working with before you start multiplying by pi.
And that brings us to the end of our journey today. So, looking around your own environment right now, whether it's the sweeping curve of a driveway, the arch of a doorway, or even just the layout of a dining table, what other curved, real-world spaces could you now mathematically conquer using just a radius, an angle, and the power of pi? Keep exploring, keep measuring, and I'll catch you on the next one.